Use binomial expansion to show that this thing is approximately equal to this thing, given that the absolute value of x is less than 1. So let's think about this to start with. We're going to use binomial expansion. We're going to use the extension of the binomial theorem from this formula here. We're going to start by rewriting this as the square root of 1 plus x over the square root of 1 minus x, which is 1 plus x to the half over 1 minus x to the half, which is 1 plus x to the half times by 1 minus x to the minus a half. Now that we've got these two, we're going to expand each of them. So I will start with this one. 1 plus x to the half. Now using the formula that we know, a in this case is 1, so it's just this bit in the bracket. It's going to be 1 plus a half times x plus a half times minus a half over 2 factorial times x squared plus a half times minus a half times minus 3 over 2 over 3 factorial times x cubed, continuing on forever, which we will simplify down to 1 plus x over 2 minus a half times a half is a quarter, divided by 2 is an eighth, so x squared over 8. And actually this one we don't actually care about because we're only trying to show up to the x squared term anyway, so continuing on like that. Now let's look at the second one. 1 minus x to the minus a half is equal to 1 plus n is minus a half this time times x plus minus a half times minus 3 over 2 over 2 factorial times minus x squared, and actually that should also have been minus x there, plus minus a half minus 3 over 2 minus 5 over 2 over 3 factorial times minus x cubed. Again, we're only actually interested in the first 3 terms, so it's 1, this is going to be plus x over 2, this one's also going to be plus 3x squared over 8. Now actually coming back to what we're trying to do, now that we know those two expansions, we can come back to our original thing, which is that, let's go back to the right color, 1 plus x over 1 minus x is equal to the product of these two things. So it's equal to 1 plus x over 2 minus x squared over 8. Well, I'll do the plus dot 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 times by 1 plus x over 2 plus 3x squared over 8, continuing on forever. Doing this expansion, we get 1 times 1 is 1. 1 times x over 2 is x over 2. 1 times 3x squared over 8 is 3x squared over 8. And then x squared over 2 times 1 is, sorry, x over 2 times 1 is x over 2. X over 2 times x over 2 is x squared over 4. X over 2 times 3x squared over 8 is going to be 3x cubed over 16. And then minus x squared over 8, and we'll do that times 1, minus x cubed over 16, and we do this one times that one, and minus 3x to the 4 over 64, and that's going to continue. Now we're only interested in the ones up to x squared, But let's simplify this. That's 1 plus x over 2 plus x over 2 is x. And then the x squared, we've got 3x squared over 8 plus x squared over 4 minus x squared over 8. So that's 3 over 8 minus 1 over 8 is 2 over 8, which is a quarter. And then a quarter plus another quarter is a half. So we've got a half x squared. And then some x cubed terms, which actually I'm not particularly interested in, but 3/16 minus 1/16 is 2/16, and then minus, and that's it. Although we would have ended up with some more when we do the x cubed terms, we haven't got all of them, but that's up to the x squared term. And if we look back at what we were trying to show, that is exactly what we were trying to show. So we have completed that step. The last thing is just to look at that interval of convergence, remembering that both of these are only true if x, the absolute value of x, is less than 1. So that is our interval of convergence. That is the interval of convergence for the green one. It's also the interval of convergence for the blue one. And because it's the same for both of them, it's the interval of convergence for this whole thing. If they were different, we'd have to think very carefully about which one would apply. Given they're both the same here, this is our interval of convergence. So here we can see how we can use this to simplify quite relatively complicated ideas or expressions, the square root of 1 plus x over 1 minus x, into a polynomial. And this is the real power of this whole process. The reason we use this process is to take relatively complicated things and to simplify them into a polynomial, which are very easy to work with. Historically, the reason for this was quite difficult to calculate. Square roots are difficult to calculate without a calculator. Obviously now we have calculators, so that's no longer true. But there are other areas of maths, such as calculus, which we'll be coming on to in a few units' time, which working with polynomials is really, really easy. But working with other functions can get a little bit complicated sometimes. So being able to rewrite this in this form means that we can use calculus on this form, which is really easy, rather than having to use calculus on this form, which is much more difficult. So being able to write these more difficult expressions as a polynomial has real benefits when we try to do some more advanced mathematics, because it simplifies our work.